Hello, hello, hello. My name is Norman LeMay and I am your statistical instructor for this video. In this video, I would like to talk about hypothesis testing, where we have two populations regarding the means, but we have dependency going on between our two populations. This is also known as, aka, a matched pairs design. All right, so in this video, what I'd like to do is to lay the foundation for the matched pairs design and then let you take a look at the other videos for the computational aspect, because some of these computations are going to be a little bit nasty regarding some of the formulas. Ooh, can't get it right. So regarding some of the formulas. All right, so without further ado, let's get started. Cue the music. All right, so how do matched pairs come about? Where do they come from? Why are we interested in them? What's so great about them? Well, they actually come up quite a bit. So let's suppose that you are the miracle pill person. And what you have found is that you think you have the best pill that will, you got it, weight loss. Cue the music. So suppose that you get a group of, say, 10 or 15 people, I don't know, 20, 30, and you bring them in and you check their weight, and then you wait an allotted amount of time. And then at the end of that time, maybe you do some follow-ups with them. You know, during that time, you just don't want them to go crazy all by themselves and not check in with them. You know, so maybe you have one or two, twice a week, twice a month meetings, but the idea is that at the end of an allotted amount of time, say 3 months, then you go back in and you take their final weight. So the question is, does your pill work? All right, or maybe you are interested in whether the heights of a child along with their same gendered parent, is there a relationship on average between the heights? Say, for example, a mother and daughter, or a father and a son. So one of the populations would be considered the parent, and the other one would be considered their child. And then finally, one that we're going to take a look at a little bit in detail, going to be our working example, is in education. So maybe the colleges come up with this grandiose little program, and they want to know, is it going to help? So one of the things that you can have the students do is grab a handful of students and have them attend some sort of a study skills seminar, teach them how to study. So at the end of this, then you'll wait an allotted amount of time, say maybe 3 or 4 weeks, and then you go back to those people and ask them how much are they studying. So before the study starts, you collect some information, say, how long do you study on average? Give your best guess. Of course, here you can get some sort of response bias, something you have to be careful of. They don't know, so they'll guess. They want to make themselves look good. So you got this initial population of how much they study before attending. So they attend the seminar, and then after the seminar, you send them on their way. And maybe a couple, 3 weeks later, you come up and say, hey, by the way, how many hours have you been studying per day or per week on average, or yada, yada, yada. Okay, so those are some ways that matched pairs design can come into play. All right, so our next part here that I want to talk about is jumping to our example. As an aid for improving student study habits, 9 students were randomly selected to attend the seminar on the importance of education in life. The table shows the number of hours each student studied per week and after the seminar. So now we want to jump down here. Did attending the seminar increase the number of hours that students studied per week? So let's take a look. Here is our initial data. So our data is the hours before. So we will consider the before hours population 1. And then we come back 3 weeks, 4 weeks later, give them some time to get it implemented and ask them, hey, how many hours are you studying now? So we have this new data set. Now, without going into the gory details, one of the things that we do when we have a matched pairs design, all right, and there's reasons to do this, is we form the differences between the data values. And when we form the differences between the data values, it gives us a new data set. So let's take a look at the differences. So here, if you take 9 minus 9, you get 0. And 12 minus 17 gives you a negative 5, and so forth. All right, so this new set of data, these differences, forms a new data set and is now based on these differences that we are going to perform our hypothesis tests on those differences. All right, so before we get into some stuff, I first would like to take a look at some terminology here. All right, so we need to talk about some terminology, and then we'll get into our hypothesis test and then everything after that. So when discussing differences, we denote the difference, the individual data value of the differences, as d sub I. And then let's just note that when we talk about the mean of the differences, we denote that as mu sub d, and we define that to be mu1 minus mu2. With the differences in the data, once we then get the differences from the data values, then we can compute our summary statistics. And one of the things that we get is this thing called d bar. So let's just note that d bar is the mean from the data of the differences. And then the next thing that we have is the standard deviation. So one of the things we can talk about is sigma sub d, which would be the standard deviation of the differences, but we don't know what that is going to be or what it is, but we can talk about s sub d. All right, so note that s sub d is the thing that we can get our hands on because it's the standard deviation based upon the data values. All right, so now that we have that information going for us, let's just recall that the question at hand was whether or not attending the seminar, did it increase the number of hours that a student studied per week. So when we come back and we take a look at our data values here, let's just note and let's just play for a moment devil's advocate. All right, devil's advocate. So let's just assume that it didn't work. So if it didn't work, if I took a look at the before numbers and then I took a look at the after numbers, and under the assumption that this thing did not work, then wouldn't you expect the before and the after to be fairly similar in values? So notice that when I take the differences, they should all be kind of hovering right around 0. All right? And notice that when I take the mean of a bunch of numbers hovering right around 0, wouldn't it make sense that the mean would probably be 0? Now, let's suppose, on the other hand, that the seminar worked. Then if I take a look at my before and my after numbers, if the seminar worked, then I would think that the after hours studied should be larger than the before. So that being the case, when I go before minus after, then those differences, I would expect them to be smaller than 0, or they should be negative. Okay, and we're going to take a look at this here in a little bit. Now, that being the case, the null hypothesis is kind of that hypothesis where Let's assume that it doesn't work. And if it doesn't work, then shouldn't mu1 equal to mu2? And if it did work, then mu1 should be smaller than mu2. All right, so that is kind of a way of writing the null and the alternative hypothesis regarding an initial sort of thought. But notice one of the things that we can do is bring the mu2's over to the other side. So this will give us our null in the form of mu1 minus mu2 is equal to 0, and then mu1 minus mu2 is less than 0. But now let's just recall, we said that mu1 minus mu2 is the mean of the differences. So notice on the left side, we can rewrite the null hypothesis as mu sub d equals 0, and the alternative in the form mu sub d is less than 0. All right, so now that we have the null and the alternative kind of figured out here, and we have some other things going on, now we have to take a look at some distribution properties regarding all of this. So under the assumption that the differences, remember, not mu1, not mu2, but the differences, the d's, under the assumption that this thing follows a normal distribution, we kind of have an idea that the mean is going to be 0, all right? Because that's what we're hypothesizing. So we're saying, hey, the mean is going to be 0. In other words, that's no, there's no difference. No, the weight loss pill didn't work. No, the study session didn't work. No difference between the heights of a parent and the same gendered child. So what we can do now is under that assumption tells us that our test statistic then is going to be in the form z sub ts is going to be d bar minus mu of the differences under the null hypothesis divided by sigma sub d divided by the root n, our typical standard z-score, z test statistic. But let's just recall, we don't know the standard deviation, sigma. So we get rid of that, just blot it all out, and we will then replace the sigma by s. So now our test statistic becomes our t sub ts. We now have the t-test statistic, and our t-test statistic is d bar minus mu of the differences under the null hypothesis divided by s sub d divided by root n. All right, and again, this is going to be on the degrees of freedom of n minus 1. Okay, but let's recall that mu sub d under the null hypothesis is equal to 0. So we can get rid of that, and notice now our t-test statistic is now d bar divided by s sub d divided by root n. All right, so this becomes our new test statistic, and the degrees of freedom is n minus 1. So that's what everything now all boils down to. So manually, you will state the null and the alternative hypothesis. And again, normally we do this in the form of mu sub d. Now, doing the mu1 equals mu2, are you incorrect? And the answer is no. But just make sure you can swing both ways, if you will. Remember, you have to come up with this test statistic. This is something computational. I don't expect you to use your calculator, but make sure, it'll get a little messy, all right? But just make sure you use some sort of technology. And to interpret that t-test statistic, remember the t-test statistic tells you how far away from zero that d bar really is. All right, so if it's far away, then yeah, something is in the data saying, no, something's going on, and it's showing evidence to support the alternative, so you reject the null hypothesis. All right, so that's the test statistic. Or if it's not that far away, it's too small, then you fail to reject the null hypothesis. And when you fail to reject the null hypothesis, then you're just saying, well, even though d bar and mu under the null hypothesis is not exactly the same, all we're just saying is this is just due to this innate random variability within the data set. All right, so that concludes this video. And as always, the technology, either StatCrunch or the TI calculator, will help you out. All right, so as always, I will see you in the classroom. Cue the music, Maestro.